Okay. So, uh, so the second derivative. Mm. Okay. So what is the second derivative? So, well, as of now, we have talked about the so-called the partial derivative. The partial derivative is especially for any given real valued function, then real valued multivariable functions, then, well, you can consider their partial derivatives. And the partial derivatives, they are also they are all still real valued functions with the same number of variables. So therefore, you can also try to take the another partial derivatives of the partial derivatives. So by doing so, we can get the higher derivatives for a multivariate functions. Uh, okay. So first, today, uh, I want to talk about the higher derivatives for two variable functions, two variable real values functions. Then, what is its partial derivative? Is going to be this. Okay, so f is a two variable functions. Oh, well, because, well, it says it's defined on a xy plane. And so, and, well, suppose that their partial derivatives, the f of x and f of y exist. And then also, moreover, let us assume that these two guys, they are still continuously differentiable functions. Then this guy can also have its own partial derivatives, and this guy will also have its own partial derivatives. So, therefore, the partial derivatives of these two guys, they are denoted as fxx, so and fxy, fyx, fyy. So we will have these four partial derivatives, right? So fxx means, well, you have taken two partial derivatives with respect to x's, and this represent you have taken the partial derivative x first and y later, and this is y first and x later, and this is what taken partial derivatives with respect to y two times. So these guys are called the second partial derivative. So basically, so in principle, for any given such a function, then you have these four different second partial derivatives. But, well, it turns out to be, so if your function is nice enough, then this guy and these two guys, fxy and fyx, they are actually the same thing. This is called the Clarius theorem. Yeah, I do not remember his name, but yeah. That can be summarized like this. Yeah. Okay, so we are now talking about a function which is twice continuously differentiable. So that means, well, this guy f, so being twice continuously differentiable means these four partial derivatives, these four second partial derivatives, they exist and they are all continuous on some open domains. In this case, fxy is the same as fyx, right? So basically, this means the order of the derivation doesn't matter. So what really matters is the number of the variables and how many times you have differentiated. Okay, so all right. Well, because of this reason, so from now on, we will not be taking too much attention towards the order of the partial derivatives. So fxy is always assumed to be the same as fyx. Okay, so what is the proof of this? Well, this proof requires just a little bit of analysis, but well, I don't think studying too much about that fits our educational purpose. So please allow me to skip it. Okay, all right, sorry. Anyway, so let us take this for granted. So if you're interested, then you may go back to this section and actually the theorem 3.9 is about the mean value theorem for the multivariable function. And if you read it and if you read the proof of this, then this is not a big deal. Okay. So for now, okay, let me skip this. All right. Okay, so and today we're on the section 3.4, which is about the inverse function theorems. In this section, so I will try to introduce two big theorems, but without any justification, because trying to prove these two guys will take too much time and effort, and I am still already running behind the schedule. Okay, so I will try my best to understand the theorem, because being able to make use of these two theorems is what really matters for our practical purpose. Okay, so first I will start introducing the inverse function theorem. So do you remember the inverse function theorem in the freshman calculus? Yeah, it goes like this. Yeah. Okay. So this is our original the freshman inverse function theorem. Suppose that I have a single variable real valued function f, and say that this function is continuously differentiable at some point. And this is very important hypothesis. And also let us assume that this guy it has non-zero derivative at this point. Okay. Well, so having non-zero derivative means, at this point A, your function is either increasing or decreasing. It cannot be constant, right? So that means if you just focus on the small interval containing A, then your function is locally increasing or decreasing. That means your function must be a one-to-one function on this interval. So therefore, that means you must be able to find an open interval I containing this point, and your f must be invertible at this point on this interval. So okay, so you can find an open interval. Okay, you can find open interval, and on this interval, your function f in this interval should be containing this point, and on this interval, my function f is invertible, and I forgot to mention this, and this inverse function is also differentiable. Yeah, and the derivative of this inverse function at this point, f of a, is actually the reciprocal of the derivative of f at a. Okay, this was the inverse function theorem from the freshman calculus. Okay, for those of you who do not remember this, I prepared a little picture of this. Okay. So, all right, sorry. So this guy, let me say this is y is the graph of y equals to f of x. And okay, now I want you to focus on this point. When x equals to a, this is the slope of the tangent line at this point, and and since this is not a horizontal line, therefore the derivative of at this point is non-zero, right? So therefore, this function on the neighborhood of this point, this function is locally invertible. So therefore, this guy would be the graph of its inverse function, right? Okay, now, and this is the inverse function. Now, I am interested in the rate of change of your inverse function at this point, f of a. And well, because of our picture, the slope of the tangent line look like this. And well, if you look at this picture very carefully, then slope of this guy should be precisely the reciprocal of the slope of this guy, right? This is what the inverse function theorem is. Okay. So this is the inverse function theorem for a single variable function. And what you're going to do for today's lecture is the inverse function theorem for multivariable functions. As always, the inverse function theorem for two variable function. Where is it? Okay. All right. Okay. I have a continuously differentiable function. F is a function from R2 to R2. So two variable functions, but this is two variable, a vector value function. So from R2 to R2. So, well, the dimension of the domain and dimension of the codomain, they must agree. And suppose that at this point, well, this is the point of interest. And suppose that the matrix derivative of your function, f, at this point is, this guy is a 2 by 2 matrix, right? Because it's from 2 to 2. So, and suppose that the matrix derivative at this point is an invertible matrix. Then in this case, you can find a sufficiently small neighborhood around A. And on this small neighborhood, my function is locally invertible. Therefore, this function must allow its own inverse. Okay, so this is what the claim of the statement is. Okay, so yeah, so you can find the small neighborhood around A onto a set of point in U plane. Okay, so all right, and also this inverse function is also differentiable. Differentiable at this point, f of A, and the matrix derivative of this inverse function. Okay, hey, what is this? So since this is a function from R2 to R2, therefore the inverse function, so which is denoted by G, is still from a function from R2 to R2. So this matrix has dimension of 2 by 2 matrix. So and this 2 by and it says the matrix derivative of this inverse matrix at this point is the inverse matrix of this original matrix derivative. Okay. So I really want to give you a couple of seconds to understand the theorem, and I hope to realize the similarities between this inverse function theorem and our freshman inverse function theorem. Okay, because here, so f is differentiable, and we are assuming that the derivative at this point was non-zero. Then my function was locally invertible, and that function was still inverse, also differentiable, and derivative was the inverse of the previous derivative. And same is true for this case. Well, my function, if my derivative, if my matrix derivative is invertible, then f is locally invertible, and this inverse function is differentiable, and is the derivative of the inverse function is the inverse of the original derivative, which is the precisely same idea. Okay, all right. All right, yeah. All right. Yeah, this is very small exercise on the inverse function theorem from R2 to R2. Well, I have some weird looking function. Yeah. Well, this is obviously not a linear function because it involves the square, the term with the squares. So this is not a linear function. So basically, this function, so in principle, so this function is very hard to deal with. And anyway, the question is my function f, so obviously it takes the two variables and it's going to give you a two-dimensional vector. So this is the function from R2 to R2. And we are wondering that either whether or not that the function f is locally invertible around this point, 1, 1. And if this is locally invertible, then I am supposed to find the matrix derivative of that local inverse function around at this point, f of 1, 1. What is f of 1, 1, by the way? If I plug in x equals to 1 and y equals to 1, then it's going to be 1. The x coordinate is 2, and y coordinate is 6. Okay, yeah, all right. 2, this is 2 and 6. Yeah, so I want to find the matrix derivative of the inverse function at 2, 6. Okay. So how do I know that? Okay, easy. This is the matrix derivative. So first component function taken derivative with respect to x goes to here, and taken derivative with respect to y goes to here, right? And same is for the second component function, taken derivative with respect to x here and y there. Okay, so I guess at this point, now you guys are all aware of how to find this matrix derivative. And let us plug in x and y equals to both 1 and 1. Then you're going to end up with this matrix. And how do I know this matrix is invertible? And you have to remember, any given matrix is invertible if and only if its determinant is non-zero, right? So in order to check if any given function is, any given square matrix invertible, then you are supposed to compute its derivative and make sure that determinant is non-zero. In this case, the determinant of the 2 by 2 matrix is this guy times this minus this guy times that. So which is 6 minus 0. So which is 6. And this is the determinant, and obviously this number is a non-zero number. Therefore, this proves that this matrix derivative at this point is an invertible matrix. And so because of that, because since this is invertible, therefore f is locally invertible. So in this case, you must be able to find some open neighborhood at around this point, and on that open neighborhood, your function is an invertible function. Therefore, if f allows its own inverse, and what is the matrix derivative of this inverse function? Then the f inverse at f11 this guy turns out to be 2, 6, right? And our theory says the matrix derivative of this inverse function is simply the inverse matrix of the original matrix derivative. So therefore what you're supposed to do is find the inverse matrix of this guy. And do you know how to find the inverse matrix of 2 by 2 matrix? Yeah, I think you are. So the determinant of this matrix times, so these two guys must be swapped, and these two guys must change their signs. So this is the inverse matrix. So I say this guy should be the matrix derivative of your inverse function at this point. Okay. Okay. Not a big deal. Easy. All right. Yeah. So this is about the inverse function theorem for of a function from R2 to R2. Now I want to generalize the theory. What about function from Rn to Rn? And there is the another statement. All right. So this is the generalized version of the inverse function theorem. Well, I have a f, and this f has n component functions from small f1 to small fn. So therefore, it looks like its codomain of this guy should be in Rn, right? And it also says that this function is continuously differentiable function on open set O in Rn. So therefore, if this is a function from Rn to Rn, right? And if the matrix derivative of this guy at this point is invertible matrix, yeah, this guy should be also square matrix. And if this square matrix is invertible matrix, then the F must be locally invertible, and the matrix derivative of this local inverse at this point turns out to be the inverse matrix of this guy. Okay. So that means if you know how to find the inverse of this n by n matrix, then that is going to be your matrix derivative of this local inverse function at this point. Okay. Okay, so we are going to accept these two theorems without any justification. So please take these for granted. All right, okay. Okay. Okay, so this is about the inverse function theorems. And now we are about to turn to the implicit function theorem. The implicit function theorem. Well, I say there are two different ways to define a function. So the most obvious way is, well, you just write down f of x equals to, well, this is how you usually define any given function. But there is another way to define a function. That is, if you give a relation between these two variables, x and y, well, so this can be any relation. So it could be x squared plus y squared equals to some number, or x plus sine of y equals to something. Well, this function f can be anything. Well, and by imposing a relation between x and y, then this is your another way to define a function. Why? Because if you can solve this guy for y, so for y, then probably you will end up with this expression, and this is how you define a function. And the first way, we usually say this is an explicitly defined function. And the second way, we say this is implicitly defined function. And same is true for the multivariable calculus. Well, any given function, y can be, so x is some vector and y is another vector. And if vector y is defined like this, then this is a explicitly defined function, multivariable function. And well, in this case, we can say this is, and if you can solve this relation for vector y, then we say this is implicitly defined function. Okay, so today we are going to study when, well, for any given relation, solving for y, is it always possible? Well, we're going to see. And in this case, what is the derivative of this guy? We're going to find out. So the differentiation theories on this implicitly defined function. So this is what you're supposed to study for today's lecture. Okay. So we start from this example. We consider a level set. So, well, x squared plus y squared plus z squared. So this is our function, three-variable real value function. And, well, and since we are looking for set of all points such that the function value equals to 3, yeah, so this is clearly the very typical level set. And we want to solve this equation for this last variable, z. Then what would you get? Then z must be plus or minus square root of 3 minus x squared plus y squared. Yeah, this looks very nice, but this guy is not quite good enough. Not quite good enough for our purpose because, well, solving any given equation for z means, and well, this means this is a function, right? So, therefore, and the right-hand side of this guy is not a function. It has a sign ambiguity, right? So therefore, for any given, in order to be a function, then for any given x and y, this number, z, must be well defined. But however, in this case, even if you have plugged in some numbers, x and y, but this, because of the sign ambiguity, so this number is not well defined, right? So this is not very satisfactory in our scenario. So in order to avoid such a sign ambiguity, we actually need to specify a point. So around that point, and if the function gxy is well defined, then we can say we are able to solve this equation for letter z. So so this is not good. Because the right-hand side is not a function. So, the same question, but this time around, we are going to restrict ourselves a little bit. So this is I want you to consider this point, 1, 1, 1. Well, x is 1, y is 1, z is 1. And if you plug in this point into this function f, then the function value is 3, right? So therefore, this is the point in this level set, right? And instead of naively solving this equation for z, now I want to solve the same equation for z, but this time around this point. Okay. What do I mean by this? So around this point, that means okay. So this is the level set. X squared plus y squared and z squared is 3. This is our level set. But here we are focusing on that we want to solve this we want to solve this equation around P. P must be a point at this point around here, right? P is, say that this is our point P. Then around this point, that means you can find some open neighborhood of this point, and the intersection of this open neighborhood of P and this level set would be some patch of this graph, right? This much of the graph. And this graph can be understood as the graph of some two-variable function, right? Right? And what function? What is the domain of such a function? Must be the projection of this patch of the graph onto the x and y plane, right? So therefore, I was able to find a two-variable real valued function whose domain is around, well, this guy, which is on the x and y plane about the point 1, 1, and whose codomain must be some numbers about the z component of this point, right? And by doing so, this guy can be understood as a graph of some two-variable function. Which two-variable functions? I guess that must be this, right? So solving some level set, solving some equation for z around the point P means that you can find some open neighborhood of this guy, and the intersection of this open neighborhood of this graph, the open neighborhood and this level set. If this guy can be understood as the graph of some another two-variable function, then I say, then I was able to solve this equation for letter z. Okay. So in this case, so this is our function g. Now I can finally say this is a function. This is a well-defined function, right? For any given point x and y on this domain, then you can always find a well-defined number for every point on this open set U. So this is function. The function g is a function from open set U to R. So yeah, this is g is a function from R to R. And being able to find such a function g, and the graph of this guy, the graph of this two-variable function, z equals to gxy, must be the same as, well, at least around this point, the graph of this guy must be the identical to this level set, right? So, and in mathematics, we say, so f, x, y, z. So this level set was originally f, x, y, z equals 3. But replacing the z coordinate by the function g is the same as x, y, and gxy. Okay, so this is what I mean by solving any given equation for level z. So okay, let me summarize this. Sorry, yeah, it took a little too long time. for if any given, suppose that this equation is given, and well, being able to solve this equation for z around some point means that you can find some open neighborhood of this point, and on this open neighborhood, the intersection between the level set and this open neighborhood, if this intersection can be understood as a graph of such a two-variable real value function, then we are okay to say that this guy can be solved for z around the point P. Okay. All right. Okay. Yeah. So, so in general, okay. All right. So, sorry. Given okay, suppose that a function is given and the level set has been defined. And well, so this is the equation. And suppose that I want to solve this equation for letter z around some point of this level set. So, well, in order to do that, first I will need to fix some point in this level set. And solving this equation for z around P, near P means, first, you must be able to find some open set U. So in this picture, yeah, this is my open set U. This is the subset of R2. And well, on this open domain, I can define a two-variable real value function G. And well, there is another open set V containing this point, and the intersection of this open set and this level set is the same as the graph of this two-variable function on this open set. Okay. So, in other words, fx, y, yes, here the z component, the z coordinate has been replaced by g of x comma y, and if this guy is the same as fp, so this is the level set, right? So this means the level set. So if you can find such a three things, open set U, open set V, and a function G satisfying the condition number 3, then we can say, haha, we were able to solve this equation for Z around P. Okay. Okay. All right. So in our example, this sphere was the level set, and we try to find the solve this relation for around this point. Then this is the open set V, and this is open set U, and on this open set, the graph of this function G, so which was this graph of this function was the same as the level set. So in this case, we were able to solve this relation for equation for letter V around this. Okay. Great. Okay, so this is the definition of being some equation. So this is the meaning of the some equation is solvable for letter Z around P in this level. Okay. And this is okay. Now, here goes the very important questions. Okay. Suppose that you have some random equation on 3 variables like this. x squared plus y squared plus z squared plus 3. Suppose that you have some random equation, and suppose that you have chosen any arbitrary point on this level. Then can you always solve the equation for letter z for any given point p in the level set? Solving for, given an equation, solving for z near any point in the level set. Is that possible? The answer is no. Why? So this is question. Is it possible? Sorry. Given an equation f x y z is k, is it possible to solve for z near any point p in Sk? The answer is not necessarily. I mean, no. Okay. Sorry. Allow me to draw a picture. Yes. Let me go back to our original example. X squared, y squared, z squared is 3. Well, even if this very nice and easy example, there is some point in this level set on this sphere, and on this point, solving for z is not possible. Can you recognize any? 여기 이 되게 쉬운 example에서조차도 g 베리어블에 대해서 푸는 게 불가능한 포인트들이 있어요. 그 이 포인트들 근처에서는 g에 대해서 푸는 게 불가능해요. 어떤 포인트들일까요? 그쵸. 여기 적도에 있는 모든 포인트들에서는 변수 b에 대해서 풀어내는 게 불가능해요. 왜 그런지 혹시 이해가 되시나요? 왜냐면은 여기 적도에서는 적도에 있는 포인트들에 대해서 오픈셋을 하나 잡으면은 스타워즈에 나오는 그림이거든요. 네, 여기 그러면은 이렇게 생긴 어떻게 보면은 그러니까 그림을 확대해서 이렇게 생긴 녀석이 이제 오픈셋 V와 점 레벨셋과 인터섹션이 되겠죠, 그렇죠? 점 P가 여기 있고, 그렇죠? 요 P가 여기로 하고, 그렇죠? 그러면은 이 녀석은 어떤 함수의 어떤 이변수 리얼 밸류 펑션의 그래프로 나타낼 수 있는 친구가 그렇게 될 수가 없어요. 이 오픈셋 V를 아무리 작게 잡는다 하더라도. 왜 그렇죠? 이게 그래프가 이게 이변수 함수의 그래프는 언제나 이렇게 혹은 이렇게 돼 있어야 되지. 이렇게 쉬운 말로 하면 어떻게 보면 이 점 근처에서는 함수의 그래프가 이제 수직이잖아, 그치? 이변수 함수의 그래프는 절대로 이런 수직 형태로 나타날 수가 없잖아. 그치? 그 이유 때문에 그래요. 그래서 적도 부분에 있는 점에서는 변수 g에 대해서 푸는 건 불가능하다. 물론 이 경우에는 변수 x나 y에 대해서는 풀 수가 있겠죠. 그렇지만 g에 대해서 푸는 건 불가능하다. 그래요. Okay, so well, around this point, this equation is solvable for variable z. But, well, for any point on this equator, I mean, so here I have chosen this point. Well, yeah. Well, since the z coordinate of this point equals to 0, yeah, so I think this is a point on the equator. And on this point, you can never be able to solve this equation for z, no matter how small your open set v is. Okay, so because, well, even if your v is so small, but around this point, this intersection of this open set and this level set should be always look something like the vertical. So therefore, this guy can never be understood as the graph of any two variable function. Okay, so what makes such a difference? So, all right. So, well, I told you if your graph is something vertical, then yeah, I told you that graph cannot be said a graph of any two variable functions. But here I want to be a little bit more. I want to refine a little bit more what I mean by your graph is vertical. Okay, what do I mean by what do I mean by? So how can I mathematically precise when I say my graph is vertical? Your graph is vertical at this point if and only if your tangent plane at this point of this level set is vertical, right? And what do I mean by a plane is vertical? A plane is vertical if and only if the normal vector of the plane has 0 z component, right? So a plane, I say that is vertical if the normal vector of this plane has 0 z component. So, well, okay, So therefore, in order to tell if suppose that you have some equation, suppose that you have some plane, then how would you tell if any given plane is vertical or not? The answer is try to look for the z coordinate of the normal vector. Okay. Okay. All right. Yeah. I have prepared many pictures. An equation of a tangent plane. Well, so this is the point Q. Yeah, this point, I'm going to name this guy to be Q. At this point, the tangent plane at Q does not have the z component. I mean, the f of, well, oh, so sorry, I messed up. Sorry, should be the normal vector. Right? Yeah. Normal vector of the tangent plane at Q does not have a z component. But, well, do you remember this? Well, for any given, so how would you find the normal vector of any given tangent plane of any level set? That can be easily found by computation of the gradient vector, right? For any given level set, and suppose that the point P is a point on this level set. How would you find the equation of the tangent plane at this point? So because we know the normal direction of the tangent plane at the point P is precisely the gradient vector. This was the normal direction, right? This is the normal direction of the tangent plane at point P of this level set. Therefore, previously, when the point P is 1 and 1 and 1, so the point at the point P, the tangent plane was not vertical. This is somehow slanted, but this is not vertical, right? And in this case, well, this is my f. Therefore, the gradient vector is 2x, 2y, and 2z. This is the gradient vector. And when x, y, z, they are all 1 and 1 and 1, then the last component, which is 2z, but z component was 1, z coordinate was 1 at the point P, and which is clearly a non-zero number. Therefore, at that plane, on that point, the tangent plane was not vertical. But however, in the point Q, whose z coordinate was equals to 0, right? And if you plug in z coordinate equals to 0 at this point, then the last component of the normal vector, normal direction, should be 0. Therefore, on that point Q, the equation of the normal direction of the tangent plane has 0 z component. This tells us, this explains why your function, why my equation is not solvable for letter z around point Q. Because this guy cannot be understood as a tangent plane for any given graph of this function. Sorry. I messed up. Yeah. This is not P. This should be Q. Q. And at point Q, so this last component of this normal direction equals to 0. So this guy cannot be a tangent plane for a graph of any two variable functions. Okay, in equations, yeah, I can explain like this. So in our case, the f was x squared plus y squared plus z squared, and is the last component of the gradient vector, which is fz. And at point P, the last component was 2, which was non-zero. And at point Q, the last component equals to 0. So therefore, this explains why my equation is not solvable for letter z around this point. Okay. Good. Great. Here, well, even though I have spent too much time explaining on this very specific example, but same idea is true for any equation at any point in the level and any value. Suppose that you have, so say something like this. Suppose that you have some level set, x squared plus 2y squared plus 3 times v squared equals to maybe 1 million. Suppose that you have such a weird level set. And suppose that you want to solve this equation for y. Then can you recognize on what point solving for y is not possible? In order to answer that, first I want you to take the gradient, compute the gradient vector of the function. What was it? Yeah. My function f was x squared plus 2y squared and 3 times z squared. You take the gradient vector and try to identify all such points that make your gradient, the y component of gradient vector equals to 0. On that point, solving the equation for y is prohibited. Right? Yeah. Sorry. Sorry. I should be writing down something. Well, say that my function is x squared plus 2y squared plus 3z squared, and say that this is 1 million. We are talking about this level set. On what point solving for y is not possible? Since the gradient vector is 2x, 4y, and 6z, Therefore, on the point where y is equals to 0, then solving for letter y is not possible. Okay. So, hey, what is this? This is ellipsoid, right? Yeah. Well, sorry, my picture is really bad, but with x coordinate and y coordinate, z coordinate, so right? And when y equals to, so on every point around on this circle and this on this ellipse, solving for y is not possible, right? Why? Because if this guy were, if I can solve this equation for y, then the graph around that point would be right, yeah, sorry, yeah. Because, well, sorry, on these points, solving for y is not possible because the equation, the tangent planes would look like this, right? And if your tangent planes looks like this, then this guy around this point, the graph, the part of the graph cannot be understood as a graph of any of such functions. Okay. Good. Great. Now, we want to talk about the derivative of this implicitly defined function. Okay. Now, suppose that you have some equation, random equation, and say that this random equation is solvable for variable letter z around this point. Okay. So that means at this point, fx, so f of z at this point must be non-zero, right? All right. Okay. So normal vector of the tangent plane, tangent to this point must have non-zero z component. Okay, this is what, okay. We know that for now. And we, okay, in this case, I want to talk about the equation of the tangent line, equation of the tangent plane at this point. Okay, so what is this? This is, well, this guy, this guy, this guy, they are the normal directions. And P1, P2, P3, this is the coordinate of the point where this tangent plane is passing through. So this means, this equation means the equation of the tangent plane tangent to this level set at this point, okay? So this is the equation of the tangent plane, right? So this is how you're supposed to find the equation of the tangent plane. Okay, good. Now, I want to solve this equation for letter z. So solving for this letter z, and so this guy, it goes to, these two guys goes to this side, another side of equation, and dividing everything by f of z, p1, p2, p3, then we will end up with this equation. And dividing by this number is always possible. Why? Because we have said this guy has non-zero z component, right? So therefore, this one must be a non-zero number. So dividing by non-zero number is always possible. So, and also you have to be aware that this number P3 is actually z, well, g of P1, P2, right? Right? Right, because, well, at this point, the last component, the z component can be understood as z equals to the gxy. So this is why I'm replacing the P3 by G of G1 and P1 and P2. Okay, so this is what? This is the equation of the tangent plane. And do you remember that I can get the exactly same result by using the linearization of the two variable function, right? This level set, well, at least locally, this level set can be understood as the graph of this two variable function g equals to gxy. So if I linearize this guy, at P1, P2, then this linearization would be the same as this one, right? Okay, so well, the right-hand side of this above equation must be the same as the linearization of the function g at P1 and P2, and this is the linearization. Do you remember? Yeah, this is the linearization. Now compare this guy and this guy. They must be, these two guys must be the identical expressions. Therefore, the only possible conclusion is negative f of xp over f of z of p must be g of x at P1 and P2 minus fy of p over fz of p must be the same as gy of the partial derivative of g about y at P1 and P2. Okay. Right. This gives us very striking result. Okay, so what does it mean? If my level set is solvable for variable z, letter z, then I will get this two variable function. And it turns out I can actually compute the partial derivatives of this resulting two variable function, this implicitly defined function. Its partial derivative with respect to x is this guy. And its partial derivative of g with respect to y must be minus of this guy. So, I mean, the point here is the partial derivatives of this implicitly defined function can be written as some combinations of the original function f. The partial derivatives of the original function. Okay, so now I can finally introduce the implicit function theorem. Okay. Well, f is a continuously differentiable function from this small f is a function from R3 to R, and P is a some point in the level set. So this relation means that P is some point in the level set. And suppose that at this point, the fz of P is the non-zero number. Then in this case, well, solving this relation f equation for G is possible. Yeah. So okay, so this level set, at least locally, this level set is the same as this guy. So that means you are able to solve this equation for z equals to function g x, y. Okay, so this is, well, solving for letter g is possible under this hypothesis. And in this case, the partial derivatives of g, x and y is same as minus fx over fc minus fy over fc. Okay, great. Yeah, even though we have spoken this result only for letter z, but you can do the same thing for another variable. I mean, for any given equation, then you can try to solve the equation for, for instance, letter x. Well, that is only possible when fx of p is non-zero, right? If that is true, then you can solve this relation for x equals to g of y and z. And in that case, the partial derivatives of g about y and z is going to be gy is going to be fy over fx, and gz is going to be minus fz over fx. Okay. Okay, good, good. Okay, so I have some random equation, and I want to solve this random equation for variable z near this point. Is it possible? If that is possible, let us try to find the derivative of this function g about x and y. Okay, so in this case, my function is fxyz is xyz and this guy, right? And when at this point 1, 2, and 1, if you plug in x, y, z equals to these guys, then the equals to 3. Oh, so that means this guy, this point belongs to the 3-level set of this function, right? This point is satisfying this equation. Now, taking the partial derivative of this guy with respect to z, which is xy times plus 3 times z squared, and if you plug in x1, y2, and z equals to 1, which is 5, and this is a non-zero number. So this is solvable for letter z near this point, and their partial derivatives are, which is, they're just merely computation. Negative of this guy and this one. Okay. All right. Okay, so, and now, yeah, I have 7 minutes left. So it's time to do the generalized implicit function theorem. I guess this is the longest statement in this entire textbook. Okay, good. And okay, good, good, good. All right, yeah. So, okay, so paper statement. I know that. I have a function. Well, f is the large f is a function Rn plus m to Rm. So Rm, so x1 from xn, so there we have n variables, and we have another n variables from y1 to ym. And since it looks like we have m such components, so this is function from Rn plus n to Rm. And suppose that each of these guys is set with some constant, so C1 from Cn. So what is this? So we have a system of m equations, but this is system of m nonlinear equations, right? And each of these equations, they are depending on n plus m many variables, right? And what I'm supposed to here is I want to solve these m equations for variables from y1 to yn. 그러니까 여러분 이런 거 있죠. 그러니까 여러분 혹시 비선형 방정식 같은 거 고등학교 때 같이 간단한 걸 풀어보시는 노력해 본 적 있어요. 그런데 그러니까 m개의 식이 있는데 거기 변수는 n 플러스 m개가 있잖아요. 그치? 근데 그 중에서 x1부터 xn은 그래서 상수 취급하고 상수 취급하면 하고 상수라고 잠깐 동안 취급하고 이 m개의 이퀘이션을 y1부터 ym이라는 m개의 베리어블에 대해서 풀고 싶은 거예요. 그렇죠? 이 상황이 그렇죠? 이게 그러니까 이론상 불가능하지 않겠죠. 물론 실제로 하는 거 엄청나게 복잡하게 하겠지만 그렇죠? 그러니까 m개의 이퀘이션을 x1부터 xn은 상수 취급하고 y1부터 ym에 대해서만 풀어내고 싶은 거예요. 이게 언제 가능하겠느냐. 지금 요 얘기를 하고 싶은 거예요. 이게 언제 가능하냐면은 이 m개의 거기 함수들 있지. m개의 함수들 있지. 스몰 f1부터 스몰 fn. 얘네들을 y1부터 y 그러니까 우리 이거 풀어내고 싶은 배경은 y부터 y에 대해서 그럼 이거 m by m 파셜 데리버티브 나오죠. 이 m by m 파셜 데리버티브가 이 인버터블한 파셜 데리버티브 디터미넌트가 넌제로라는 소리니까. 그렇지? 이 m by m 매트릭스가 그러니까 인버터블 하면은 이 경우에는 이론상 이 m개의 이퀘이션을 y1부터 ym에 대해서 풀어낼 수가 있다. 이 비선형 방정식의 해가 최소한 국소적으로는 존재한다. 되게 중요한 결론이에요, 이거. 사실 여러분 우리가 맨날 하는 결국 우리가 졸업하면 맨날 하는 게 거기 서양 이거 시스템 오브 이퀘이션 풀어내는 게 되게 제일 맨날 주구장창 하는 얘기예요. 근데 이게 언제 가능하냐? 요 디터미넌트가 언제로? 그리고 이때 요 y1 그럼 이제 이 식을 그래서 y1부터 y1에 대해서 m에 대해서 풀어내면 이렇게 풀어낼 수가 있다는 소리지, 그치? 최소한 국수적으로는. 그리고 이때 요 g1부터 gm이라는 함수들은 다 미분 가능하고 걔네들의 파셜 데리버티브는 요 방정식에 의해서 결정된다. 자, 그래요. 여러분 제가 2분 남았는데 진짜 엄청 빨리 할게요. 핑. 그래요? 네. 자, 티니핑 노래는 그만 부르고. 자, 이거 한번 볼까요, 우리? 여기 이퀘이션이 두 개가 있죠. 이거 다 F1, F2 무시해버리고 이거 두 개만 보자고. 이거 X1과 X1, X2, X3는 상수 취급하고 이 두 개의 비선형 연립방정식을 Y1과 Y2에 대해서 풀어낼 수 있겠습니까? 라고 물어보고 있는 거야. 그치? 어느 포인트 근처에서? 그쵸? 그러니까 1, 1, 마이너스 1, 1, 2. 요 근처에서 그리고 풀어낼 수 있다면은 이 Y1과 Y2를 풀어냈을 때 그 해당되는 함수는 그럼 Y1도 그렇고 Y2도 그렇고 X1, X2, X3에 관한 디펜딩한 함수가 될 거 아니야. 그치? 걔네들 중에서 엄청 많은 파셜 데리버티브들이 있겠지만 Y1과 Y2의 X2 두 번째 베리어블에 대한 파셜 데리버티브를 한번 찾아보자 라는 거예요. 자, 그러면은 아까 우리가 뭐였어? 지금 F1이 이거고 F2가 이거지. 그러니까 Y1과 Y2에 대해서 풀고 싶으니까 F1과 F2를 Y1, Y2, 요 Y1, Y2에 대해서 이 2x2 매트릭스 데리버티브 우리가 생각할 수 있겠지? 그쵸? 근데 요 X랑 여기 포인트는 요거 대입해주고 그러면 요런 매트릭스 나오겠죠? 요거 계산해 보면 12, 그러니까 넌제로거든요. 그러니까 인버터블한 매트릭스예요. 그러니까 요게 뭐냐면은 요 포인트 근처에서 이 식을 Y1과 Y2에 대해서 풀어낼 수가 있겠구나. 최소한. 그러니까 정답이 존재한다는 그 반증이야. 증거가 되는 거지. 자, 그러면은 그래서 이 경우에 Y1을 스몰 G1이라고 이름 붙이고 Y2를 스몰 G2라고 이름 붙일게요. 자, 그럼 이때 아까 얘 데리버티브도 이런 관계식이 성립한다고 했잖아. 지금 요거는 요 스퀘어 매트릭스는 지금 요거랑 똑같은 거거든요. 여러분들 집에 와서 한번 보세요. 그러면은 F1, X2, F2, X2 이거는 G1, X2, G2, X2 똑같다고 했으니까 결국 이거 뭐야? 이거는 F1을 X2에 대해서 편미분하면은 이거 Y2만 이거 편미분 여러분들 다 쉽게 할 수 있지? 이것도 다 할 수 있을 거예요. 그다음에 요 포인트 대입하면은 그럼 뭐가 나오냐? 요게 나오거든요. 요걸 그러니까 요 녀석은 이제 이게 역행렬이 존재하는 행렬이잖아. 그치? 이게 인버터블 하다며 요게 여기 포인트에서 그치? 그러니까 요거 G1 요 행렬 이 컬럼 벡터에 대해서 풀어낼 수가 있겠지? 그럼 요거 열심히 뚝딱뚝딱뚝딱 해보면은 요게 나와. 그러면은 자 우리가 G1 G2를 X2에 대해서만 편미보니까 파셜 데리버티브 구했는데 X1에 대해서 파셜 데리버티브 구할 수 있어야 되겠죠, 그렇죠? 여러분 제가 이런 말까지 하고 싶지 않은데 시험에 꼭 나와요. 되게 중요한 이론이거든요. 꼭 공부 좀 해주세요. 네, 오늘 여기까지 하겠습니다.